If networking is how services talk, your database is how they survive. At a small scale, storing data is simple, but at large scale, everything becomes a battle of consistency, latency, and replication. This is where system design becomes real engineering. Today, we're going to understand how databases actually think, how they scale, and how to choose the right one when the stakes are high. But before we can worry about scale, we have to address the most fundamental debate in the industry, the clash between structured reliability and distributed flexibility. When people hear SQL versus NoSQL, they often assume one is modern and other is outdated. That is not true. They're built for different design goals. Relational databases like MySQL and PostgreSQL store data in structured tables with predefined schemas. Relationships between data are explicitly modeled using foreign keys and joins. These systems are built around strong, consistent, and transactional guarantees. They're excellent when correctness matters deeply, such as in banking systems, payment processing, or inventory management. On the other hand, NoSQL databases such as MongoDB, Cassandra, and Redis were designed with horizontal scaling and distributed environments in mind. Instead of rigid schemas, they often allow flexible or dynamic structures. Many of them trade strict consistency for availability and scalability. They're commonly used in social media platforms, real time analytics systems, caching layers, and high throughput distributed applications. The key insights is that SQL databases optimize for correctness and relational integrity, while many NoSQL systems optimize for scale and flexibility. This choice between SQL and NoSQL isn't just about how we format our data, it's about the underlying guarantees the database makes to us when things go wrong. To understand database guarantees, we must understand ACID. ACID actually stands for atomicity, consistency, isolation, and durability. Atomicity ensures that a transaction either fully completes or fully rolls back. Consistency ensures that all database rules and constraints are respected after a transaction. Isolation ensures that concurrent transactions do not interfere in harmful ways. Durability guarantees that once data is committed, it will survive crashes. Relational databases like PostgreSQL are designed around these principles. This makes them ideal for systems where correctness is critical. In contrast, many distributed NoSQL systems follow base model, which basically stands for basically available, soft state, and eventually consistent. Instead of guaranteeing immediate consistency across all nodes, they guarantee that the system will eventually converge to a consistent state. This model accepts temporary inconsistencies in exchange for higher availability and better scalability. The trade off here is fundamental. You can have strict correctness or you can have massive scale with tolerance for temporary inconsistency. You rarely get both at extreme levels. But even with the best consistency model, a database is useless if it takes 10 minutes to find a single record. To stay fast, databases rely on specialized maps called indexes. Without indexes, a database would have to scan every row for every query. That would be catastrophic at scale. Most relational databases like MySQL use B tree indexes. A B tree keeps data sorted and balanced, allowing efficient searches, inserts, and range queries. It is particularly strong for read heavy workloads and ordered lookups. On the other hand, databases like Cassandra and storage engines like RocksDB use log structured merge trees or LSM trees. Instead of constantly updating data in place, LSM trees write sequentially and merge data over time. This design significantly improves write performance, making it ideal for logging systems and time series workloads. The choice of indexing structures the choice of indexing structure dramatically affects performance and characteristics. Some databases are optimized for reads and others are optimized for heavy write throughput. But even with the right index in place, your database isn't just blindly following orders. Behind every query is a complex brain making split second decisions on how to fetch your data. When you send a query to a database, it does much more than simply execute it. The database parses the query, analyzes available indexes, estimates the cost of different execution strategies, and builds a query plan. This component often is called as query planner, which decides whether to use an index, which join strategy to use, and in what order to scan tables. Two queries that look similar can have dramatically different performance depending on indexing and execution plans. Understanding how database thinks internally allows you to design schemas and queries that scale efficiently. And as expected, optimization only gets you so far on one machine. Eventually, you will hit a ceiling where a single server simply isn't enough. And that's when we have to start talking about replication. So, replication basically means copying data across multiple nodes. In a leader follower model, one node accepts writes and follower nodes replicate that data. Systems like MySQL and PostgreSQL commonly use this approach. It allows you to scale read traffic across replicas and provide failover protection. However, replication introduces lag. Followers may not instantly reflect the latest writes, which means reads can be slightly stale. In multi-leader system, on the other hand, multiple nodes can accept writes simultaneously. Distributed databases like Cassandra are designed with this in mind. This improves availability and supports geographical distributed systems, but it introduces complexity in conflict resolution. Replication always introduces trade offs between consistency, latency, and availability. But while replication copies the entire database to new nodes, what happens when your dataset becomes so massive that it won't even fit on a single disk? To solve that, we have to break the data apart entirely. So replication copies data and sharding basically splits it. Instead of storing the entire database on every node, sharding divides the data across multiple machines. Each shard is responsible for a subset of the data. You might shard by user ID using hash, by geographical region, or by data ranges. The challenge is avoiding uneven distribution. If one shard receives significantly more traffic than others, you create a hard shard problem that becomes a bottleneck. Sharding is one of the most powerful scaling techniques, but it requires careful planning and monitoring. All these scaling techniques, replication, sharding, and indexing, eventually run into a brick wall of physics and logic. This wall is known as cap theorem. The cap theorem states that in a distributed system, you can only guarantee two of the following three properties: consistency, availability, and partition tolerance. In practice, network partitions are unavoidable in distributed systems. That means you must choose between strict consistency and high availability during failures. Relational databases traditionally lean towards consistency, while many distributed NoSQL systems lean towards availability. However, modern systems often allow tunable consistency levels, blending the two depending on the use case. CAP is not just a theory, it directly affects system behavior during outages. Now that we have navigated the rules and theories of distributed data, it's time to look at the actual tools on the market. Understanding these categories is the final step in choosing the right engine for your workload. Understanding database categorizers helps you choose correctly. Key value stores like Redis and DynamoDB are extremely fast and simple. They're ideal for caching, session management, and counters. Document databases like MongoDB store semi structured data, usually in JSON like formats. They provide flexibility and are well suited for user profiles, content management systems, and evolving schemas. Wide column databases such as Cassandra are optimized for massive scale and distributed writes. They are common in logging platforms, IoT systems, and time series storage. Graph databases like Neo4j specialize in modeling relationships between entities. They excel in social networks, recommendation systems, and fraud detection where connections matter more than individual records. Each type is optimized for a specific workload pattern. We've seen the tools and patterns, but when the time comes to actually build your system, how do you even make a final call? It all comes down to a few critical questions. Choosing a database is not about trends, it's about constraints. You must ask whether your system requires strong transactional guarantees. You must consider your read write ratio. You must evaluate whether horizontal scaling is required or not. You must understand your data relationship and access patterns. And you must decide whether temporary inconsistency is acceptable or not. There is no universally best database. There are only design trade offs aligned with specific system requirements. So, from this video, we got a basic blueprint of how databases define the limits of your system. They determine how your systems behave under failure. They define how quickly you can scale. They control data correctness and performance ceilings. If you deeply understand databases, you do not just store data, you design resilient, scalable systems. And that is why this phase is the biggest one. Thanks for watching.